Okay, buenos dias. Buenos dias. I have the great honor, the great pleasure of closing this session. I hope you all have been really impacted by what seems like science fiction, right? We've been talking about AI and robotics and AR and VR. And I'm going to close this session talking about the brain. But I couldn't be in Spain and do a session on neuroscience without starting here. Does anybody know who this man is? Ramon y Cajal? Okay, when I was in graduate school, we idolized this man. Some neuroscientists consider him the father of modern neuroscience. Why? He made these stunning drawings of the brain. He was a physician, but he was an artist, and he would look at these nerve cells under a microscope, and he would draw them and paint them. This man redefined our understanding of neural circuitry in the brain. Now, there's been an entire traveling exhibit, actually, of his drawings because people felt that they merited their own exhibition. Now, why is this so important, and why do I want to open with this? Well, understand that the first thing I'm going to talk to you about is this very concept. It's actually how we map the brain. And mapping the brain is so important because if we can't read the neural code, we can't reprogram the brain. We can't write the brain. We can't create closed-loop systems in the brain. And in fact, the second scientist I'm going to put up, more than a century later, Rafael Yuste, he also trained in Madrid. Now, he's at Columbia University right now, okay? He's at Columbia. But President Obama in 2014 had tapped him to actually lead a brain mapping initiative for the United States. Now, the question is, where is brain mapping going? And what can you do with this absolutely amazing technology? So what I'm going to do for you in the very first part of this talk is I'm going to give you some examples of how you can take some of our older brain mapping technology and discover some new things. And the first place I'm going to take you is the place where I spend my life. I am not just a neuroscientist. I'm also an anesthesiologist. I work in an operating room, and I change people's levels of consciousness for a living. In fact, I give people drugs, and I take away their consciousness. And then what do? You can see in this picture here, I have electrodes on this person's forehead. I actually measure their brain as I move them from being awake and aware to losing all conscious awareness of the world and then coming back. And I do that so I can protect them from all the stimuli coming in from the outside world, things like the surgeon's knife cutting into them. But I also can do something else. We can take this data and we can write new algorithms to actually map states of consciousness in the brain. And right now we're working on some algorithms using nonlinear dynamics or chaos actually analysis to characterize where the brain goes when it loses awareness. And this is an entirely new way of approaching this problem. Okay, so that was one example, electroencephalogram mapping one of the most important problems in science, human consciousness. The second example I'm going to give you is using another older technology. It's called functional magnetic resonance imaging. Now, this example is from a lab in Berkeley. It's Jack Gallant's lab. And what he did was he took a bunch of students and he put them in a scanner to actually look at their brain activity. And he specifically was looking at the back of their head. It's a place called the visual cortex. And he presented YouTube video clips to them. And then he measured the activity coming from the backs of their brains. And then what they did in his lab was they created a data dictionary. They basically wrote a machine learning algorithm before it was in vogue to use these terms. And every line, every shadow, every shape was actually mapped in the activity of the brain. And then they took the dictionary, they put a new set of students in the magnet, showed them a new set of videos, and watch what happens. So what you're going to see is the YouTube video clip on the left that was presented to them. And you're going to see the reconstruction made from that algorithm on the right. I want you to appreciate what I'm showing you. This is actually mind reading, right? This is me taking someone like you, putting you into a machine, showing you something, and reading your very thoughts. And I'm doing this with really old technology. And why can I do this? It's because our computing power is going up like Moore's Law. And it's becoming cheaper and easier to do these things. Now, he didn't just stop there. Several years later, he decided to explore a different part of the visual system. We don't just look at colors and shapes and edges and motion. We make sense of these things. We make semantic sense of these things. So he looked at different regions of the visual system. And he started to present videos. Sorry, I'm going to go to this screen here. And you can see, here's some surf, body of water, sky, tree, cloud. He was actually able to reconstruct the meaning that the subjects were actually taking from the world that they were seeing. Now, not to be outdone, and I want you to appreciate how crazy this is, right? This is really, truly mind reading. A group in Japan decided to try to create a dream catcher. So what they did was they took their subjects, put them into a magnet, and they waited till they fell asleep. And then as they gave them some time, and then they woke them up, and they asked them to write down what it was they were dreaming about. It's like keeping a dream diary. Has anybody ever done that? Captured their dreams? Good, good for you. Yes. Anybody on this side? Excellent. It's actually, by the way, a really good thing to do because some of your most creative thoughts come during dreaming. I've solved actually a lot of problems, so I often set intentions before I fall asleep. And I actually wake myself up sometimes and write them down. Okay, so what they did was they woke them up and they asked them to write down what they were dreaming about. Okay, and they would get things like this. From the sky, I saw something like a bronze statue. They took that semantic meaning and they also correlated it with the visual activity. They were able to reconstruct the substance of their subjects' dreams. Now that's kind of crazy. So I'm telling you right now, I can non-invasively look inside your brain and decipher the meaning of your dreams. Now how many people think that's kind of cool? Okay, show of hands. How many people want me to do that to you? Okay, so I sort of subscribe to this lyric from Bob Dylan. If my thoughts, dreams could be seen, they'd probably put my head in a guillotine. Now, it's not like everything I dream is like that, but you know, I'm not sure exactly how far I want people to probe. But this idea that we can probe the brain is being taken to new heights. So this company, BitBrain, actually came out of the University of Zaragoza, and they've created a platform to create tools to do all kinds of mind reading. And one of them that might be very interesting for this audience is they've created a neuromarketing platform. A new approach to market research that allows for the extraction of emotional and cognitive information. So basically, you can measure people, not their stated reactions to things, but their automatic reactions to things. So you can use brain signals, you can use pupillary diameter, you can use how they're sweating, you can use all sorts of cues. Now last year, this scientist, Poppy Crum, she is the chief scientist at Dolby Labs, and she was on the TED stage, and she was saying, hey, guess what, guys, I've done something else. So what she's showing in this particular image is infrared imaging of someone's face. And she claims that she can completely read your emotional state by this kind of infrared imaging. So the next question I have for you is, how many of you have IoT devices in your home, like an Alexa or Google Home? You again. This side? Okay. How many of you have actually stopped to consider what kind of biometric data those devices are collecting about you? Sending them to the cloud. A few of you. Over here as well. Just remember that every update that comes into that system, every upgraded sensor, I mean, these cameras are a couple $100 on Amazon or eBay, right? These things can detect your unintentional states to just about everything you're presented with. So you're giving away a lot of data to the world. Now, this is one kind of mind reading. What else can you do with it? Well, people have tried to take fMRI into the courtroom. So one question has been, can you use functional magnetic resonance imaging, this imaging of brain activity, to tell you if people are lying or not? Can you create a lie detector? So show of hands, how many people think that's possible? You think you might be able to, okay, what about here? It's about 25, 30%. All right, so what if I were to tell you that I have, well, actually, let me ask a different question. How many of you have kids? Oh, a lot of people. Okay. How many of you have kids who've lied to you with a straight face? Okay, see? I just went, with full disclosure, I lied to my parents all the time. I used to sneak out of my house, okay? I was a really good liar, at least to my parents, but in some contexts I couldn't lie at all. If you were to image someone's brain when they're not having a social reaction to the lie, what do you think their brain is going to tell you? What happens if you were to image the brain of somebody who were autistic, who had completely different kinds of social interactions with the world? So this could be problematic. But there is another reason that this is a really big problem. All right, so I'm going to take you to the first truly science fiction-y thing I'm going to say today. And this should hopefully really freak you out. So I'm going to set up an experiment, okay? And this experiment, and this is a little hard to do on this stage, so I'm going to stand here, and I'm going to be a mouse, okay? Here's a, you still have me? Okay, here's a cage, okay? And this little part of the cage over here is electrified, has a little bit of electricity. Not enough to hurt me, just a little bit. Now, if I'm walking over here, and my paw touches this, I get a little shock, and I say, oh, I don't want to be here anymore. So I do two things. One, my brain forms a spatial map of the cage, so it knows where everything is. And the second thing I do is I have a fear avoidance response. Now, you can actually put a fiber in the brain of a rodent and record these electrical signals. So you can actually record this memory that's being formed. Now, guess what you can do with that? It's all about brain mapping. You can take that recorded memory, you can put a new cage, no electricity, new rodent, never encountered it before. You can inject the memory of the other rodent into the other one's brain. And that animal will act like this part of the cage is electrified, and they will have a fear avoidance response. So what have I just told you? You can move memories not between computer brains, from one organic brain to another. We've already done it. Okay, now these are very simple memories, but I want you to sort of keep this in mind. What else can we do with mind reading? Well, it turns out if you're wearing an electroencephalogram and type a password in, I can now read it. Okay, so I can sort of hack your brain that way. What else can I do? This researcher in New York, she found that if she actually showed certain stimuli, certain visual stimuli to her subjects and recorded their brain waves, she could identify them with 100% accuracy. Now, the EEG cap she's using has a lot of electrodes, but she started trying the experiment with wearable devices you could get on the market, just a few electrodes across the forehead. She was able to do the same thing. And in this study, the EEG was used to actually look at a group of subjects, and their brainwaves were recorded, and then they were asked, which ones of you self-identify as alcoholics? Okay, so that data was noted, and then what they did was they trained a machine learning algorithm, a classifier, on a different data set of alcoholics. And they actually were able to figure out which people in that group were alcoholics. They did not have to be actively drinking, just people who had that tendency. And then they went back to the original data set, and they could pick out the people in the new data set who had self-identified. It wasn't with 100% accuracy, but they did a much better job than chance. That should terrify you. Why? Well, what if you have a tendency towards something and you're not even doing that thing, right? What if you have a tendency towards addiction or mental illness and it's in check, or you don't even really quite know about it? That could be used against you by an insurance company, by a government. Something to think about. So as I wrap up this idea of where we've come with brain mapping, I want you to hold this in mind, right? Because we have to temper everything we say with an ethical discussion. And for those of you that have the power to capture data, I want you all to think about the awesome responsibility that comes with that. So let's move on to the next piece of this. I told you that we've been mapping the neural code, and using that information, we can turn around and do the opposite thing. We can now write the brain. So what do I mean by this? Brain is a collection of circuits. Most of the diseases that are associated with the brain are circuits that go bad. So we can actually do something with that. This is a diagram in which you see a cartoon of basically an electrode coming into deep structures in the brain. And then there's a wire that comes out, it gets tunneled under the skin, and it gets put into a battery pack that goes under the collarbone. And you can program that battery pack to deliver electrical current at a certain amplitude, patterns, frequencies. So why would we ever do something like this to someone? This is very invasive neurosurgery. Well, some people have brain diseases that just don't respond to drugs, and it's destroying their lives. You can actually stick an electrode, inject electricity into someone's brain that's gone bad, and rescue the circuits that aren't performing correctly. I'm going to show you a video so you can see this. So what you're going to see in this video is a gentleman who has something called Parkinson's disease. Okay, that's a movement disorder. And in this video, he's holding up something. That's the controller for the battery pack. What he's going to do is he's going to turn it off. You'll see what happens, and then he's going to turn it back on.
Temos uma magnética que liga e desliga o DBS. Você quer ver o que é o sofrimento? Agradeço a Deus por ter essa coisa. Olha só aqui, ó. 2 segundos.
He's turning it off.
Vai. Fica tranquilo. Agora eu estou com Parkinson. Real, é verdade, não estou mentindo. Isso aqui não é o Michael Fox com o Limbal aqui.
Liga, liga.
Isso aqui é Parkinson. Agora vou ligar de novo.
He's going to turn it back on, and the tremor's gone.
Acredite se quiser.
Right? You can get up again. Yeah. I mean, this is amazing, right? I just told you that we can implant electrodes into people's brains, shove some electricity in there, and rescue that. Okay, I'm going to tell you something else kind of creepy. We don't just stick electrodes in people's brains. We do it awake. Why do we do it awake? During neurosurgery, we map their brain's response in real time as we move the electrode into their brain. We inject currents and electricity, and then we see what the effect is. So now in the next example I'm going to give you, you're going to see a guy who's awake in the operating room. This is the assembly. There's a whole microdrive that shoves the electrode in. This guy also has Parkinson's disease, but he's a violinist. His tremor is not as bad as the other guys. So what did they do for him? At the Mayo Clinic, they brought him into the operating room with his violin. They put a 3-axis accelerometer on his bow, and they had him play the violin while he was in the operating room. And then, as they injected the electricity, they could see the tremor going away. So you're going to see a very short segment of him in the operating room, and then you're going to see what happens at the end. He's going to do the same thing. He's going to turn his device on and off. So here we go.
By measuring Roger's movements, the accelerometer told Dr. Lee if the electrodes were in the right spot.
Without the stimulator on,
same guy, 3 weeks later.
The tremor is quite pronounced.
You can see the difference. With the click of a controller, Roger can turn the electrodes on and off.
And that's as smooth of a bow as I can play right now.
So he's turned it back on now.
But when it's on, Roger's mastery of the violin is absolutely clear.
So how many people think that's kind of amazing, right? Okay, as I go through this talk, I want all of you to think, okay, he has a disease. How many of you would do this to yourself voluntarily without a tremor to improve your ability to play the violin? Show of hands. There's at least a few. This side of the room? Yeah, okay, start thinking about that. We're gonna go there, okay? We're gonna go there. All right, now, most of you are probably, the ones who haven't raised their hands, how many of you are not raising your hand because you don't want me to crack open your skull? There, over here? Okay, that's valid, right? Infection, bleeding, neurosurgery, who wants that? I'm here to tell you that the technology to deliver energy into the brain without cracking open the skull has gotten so advanced, we can do all sorts of things. One example is this, focused ultrasound. This is the same stuff that you use to image a heart or image a fetus in a pregnant mother. It's just a slightly different energy and tuning of these sound waves. You can actually stimulate the brain now from the outside using electricity. Or you can use magnets, because magnets induce electrical currents. So you can do that as well. Now recently, last summer, something else was done. So this came out of MIT. This is an example of actually, they found a way to put a battery-powered device within the brain and actually within the body that they could control from the outside of the body using radio waves. Radio waves, okay? So we're completely changing the landscape. All right, now I want everybody to think for 1 second. How many of you think you're going to live past 85? Show your hands. Oh, that's like almost everybody, okay? This side. Okay, this is great. This is a really youthful group. Okay, I like it. Okay, everybody look to your right. Look at the person to your right. Now I want you to ask yourself a question. Which one of you is going to get Alzheimer's disease? Right? You all want to live past 85. This is a problem, right? We have a problem. One of the things that longevity brings up for us is the fact that our bodies degenerate. And the organ that is most precious, that might be doing a lot of that degenerating, is the brain. All right, so what can we do? One of the things that our exponential technologies have enabled is the ability to now diagnose Alzheimer's disease very, very early. So new microfluidic technology is making it possible to diagnose things like Alzheimer's disease and cancer in a drop of blood. Something else that's incredibly new and exciting, this couple right here, they founded a company called United Neuroscience. It's actually Mei-Mei's mother, who is the chief science officer. She developed a vaccine for pigs to actually chemically castrate them, as Mei-Mei says, to take away their balls, so that they taste better. I know this sounds really weird, but apparently in veterinary science, this is a thing. Okay, so that same process can now be used to target the immune system of people who are going to develop Alzheimer's disease or are in the very early stages. And they have now been running, this just got published last month, 96% of their patients showed efficacy without side effects. That's an incredible, we have no cure for Alzheimer's, okay? This is a huge step forward. But we're here talking about neuromodulation in this section. Let me tell you what else we're going to be doing. We're going to be rewriting the brain. So Incytec is an Israeli company, and they make focused ultrasound. And they just got the nod from our regulatory body, the FDA, to actually disrupt the blood-brain barrier, the blood vessels in the brain, so that they could start draining the plaques that cause Alzheimer's disease in people who've developed it. And the very first patient just underwent this procedure last October. So we don't even know what the result is. These things are all hot off the press. All right, something else for Alzheimer's. It turns out you can actually implant fibers into mouse brains and dissolve some of the plaques that cause Alzheimer's. But again, how many people want implants? Not everyone wants their brain or skull cracked open, so this group at MIT decided they would try those same frequencies by flashing lights into people's eyes and noise through their ears. And in fact, they were able to not only dissolve some of the plaques, but improve learning and memory. And it's not just in Alzheimer's. So transcranial magnetic stimulation is now being used to treat drug-refractory depression. These are people who fail drug therapy, they fail talk therapy, they're suicidal. Put some magnets on their head in the right locations with the right stimulus parameters, and you can rescue some of these people. And so there's even a Swedish startup that says, hey, I think I might be able to do something by actually using a head-mounted transcranial electric stimulator. So that's what they're trying to do. And all those Parkinson's patients I showed you where we were putting electrodes in their brain, there may be new non-invasive therapies on the line for them, for things like the treatment of migraine diseases. And what about this thing, right? I don't know what it's like in Europe, but in the United States, opiate use has hit a crisis level. What if you could actually treat pain using non-invasive neurostimulation in the packaging of a neurowearable device? Now, there's also some direct-to-consumer stuff that's taking place. Look at this. People are doing studies to see if you can apply energy to the outside of the brain and actually improve athletic performance. So there's a whole new field. This is not pharmaceuticals. This is electroceuticals. And the number of companies coming online to deal with electroceuticals is also exponentially increasing. So this is Cognito Therapeutics. This company was born after those studies you saw coming out of MIT, in which they were treating Alzheimer's disease by flashing lights. This company, Cala, founded by Kate Rosenbluth, this came out of a Stanford biodesign program. So this is also sort of an academic to entrepreneurial transition. But there are also some huge things. So Google and GlaxoSmithKline have actually joined forces to create an electroceutical company. So this is an entirely new horizon. So next question for the audience. This is going to be as participatory as we can. Okay, how many people would let me modulate your brain if I could make you smarter? Oh, there's a big show of hands on this side. What about this side? Come on, guys. It's a competition. Okay, how many of you think it's even possible? I mean, a few of you. You know, actually, I was skeptical. I was completely skeptical. I was wrong. Okay, so it turns out you can actually stimulate parts of the brain and increase the ability for those connections that need to break and reform for learning and memory to take place, to occur. And one of the first places this has been looked at is something called the vagus nerve. It's a nerve that controls so many things in your body, including your heart rate. It runs kind of along your neck after it leaves the brainstem. And in people who've had strokes, you can actually stimulate this nerve and actually improve their rehab capabilities. But more than that, we can now non-invasively modulate the brain and improve people's cognitive capacity. So let's say you do get Alzheimer's disease, or as all of us do, as we age, you just get a little more forgetful. We can actually improve your learning and memory. In this particular study, I mean, one of the questions was, would it last, or do I have to keep on stimulating myself? Well, in this study, math capabilities persisted for 6 months after stimulation. So that's quite remarkable. But remember, we're always going to have to keep ethics in mind. We have to make sure this is democratized, because what happens if I were to stimulate your child's brain, give them 15% extra cognitive capacity? How would they outcompete everyone around them? And then what would that actually mean if you gave them that competitive advantage? Would we not want to make that available to every human on this planet? Okay, so moving on. Now we're getting into pretty creepy stuff. Connecting brains to machines. All right, so what do I mean by that? I mean literally, there are ways to connect our organic brains to machines on the outside and the inside. So, show of hands again. Does anybody, you can call this out, what is one of the oldest brain-machine interfaces we've ever had? Does anybody know? It's for a sensory system. This side? Did you just, you bang on, perfect. Cochlear implants for people who are deaf. That's exactly right. I'm going to show you a video of a child who's deaf who had a cochlear implant put in, and I want you to see the transformation that's going to take place in their brain. Don't take video of this.
And he's back on again. See how he turns?
Turn. Hi, Jonathan. Stop the sucking.
Yeah.
Hi. Good.
That's
Could you
real good.
hear that? Hi, sweetie. Could you hear that?
Okay, so that's one of my favorite videos, by the way. there's something really important about that. You saw how that child's entire face changed and transformed, right? That child's entire brain is now going to be rewired for the remainder of their life. And if they hadn't gotten the implant early, this would be very hard to recover. And we're trying this with all sensory systems. So the new wave is in the eye. So we're replacing things that have gone bad in the retina with electrode arrays. These are wired arrays. This one's from the US. The other one, retina implant, is German. And they all have FDA and CE mark now. There are now bionic versions, wireless versions of these kinds of implants for the eye that are being made. But I'm going to show you a really exciting version now. Now, this is something called sensory substitution. It's for blind people. And what you're going to see, this is from a company, Brainport, that came out of the University of Wisconsin. And essentially what you see is a pair of glasses, and on the end there's a camera, and then there's this like little paddle. So what that paddle is, it's actually a tongue depressor. You wear it in your mouth like a lollipop. Now you see that the camera over here imaged a coffee cup in grayscale. And the places that are pure white have a very, very strong electrical current. The places that are black have no electrical current. And the places that are gray are somewhere in the middle. And what you can do now, if you're a blind person, is you wear this device. Your sense of taste is much better developed now because you've lost vision. And it actually feeds in and gives you a picture of the visual world. So I'm going to show you a video of what this looks like. So this is a blind gentleman who's going to be wearing this device, okay?
Your brain is what really sees, not your eyes. If your eyes don't work, and you can create another portal into the brain, then your brain is what is going to interpret the world around you.
Brainport is essentially a camera that translates a video image to a plate that I wear in my mouth.
Dad.
So he tasted the word,
Hundreds
right?
of pixels on the plate tingle on my tongue, and together they form patterns and shapes that my brain interprets as the space around me.
I can see it, I just can't grab it.
So he's climbing a rock wall with his tongue. So I always find this extraordinary because I can barely climb a rock wall with my vision intact. So, and by the way, if you go to YouTube and you put in Brainport and climbing rocks like outside, you'll see this guy like free climbing without his vision, okay? Absolutely insane. Okay, so here's your next kind of disgusting picture. I'm showing this for a reason. That is a real brain, and those little metal things on top are real disc electrodes. This is the brain of somebody who's undergoing neurosurgery for seizure. Now, why do I show you this? I've been telling you about non-invasive, but unfortunately at the moment, the highest fidelity for reading and writing the brain is by touching the brain. It's invasive. But let me show you how extraordinary it is what we can do with that. So I'm going to introduce you to an academic consortium called BrainGate. And what these research institutions are doing is they are trying to get these electrode arrays into the brains of people who are quadriplegic. That means they are paralyzed from the neck down, okay? They can't move their arms or legs. They're cognitively completely intact, and these people know how to think about moving, they just can't move. You can take this tiny electrode array that you see right here, it's the size of a little baby aspirin, and you can put it on a strip of the brain called the motor cortex, record the signals that these people are sending. I want to move. This paralyzed woman is sending her thoughts to a robotic arm, and it is bringing a carafe of coffee to her mouth. She did it with her mind. She's moving a robot with her mind, okay? That is quite extraordinary. She had never been able to do this since she had had her stroke. Now, what if, instead of having to direct a robot on the outside, what if you could actually read the desire to move and reconnect it back with the spinal cord that had been damaged? So that's what this group in Switzerland is doing. So you're going to see a similar kind of video. This is a paralyzed monkey. You can see that this array is in its motor cortex. It's recording the signals coming from its brain. It wants to move, sending it to a decoder. There's a machine learning algorithm. And it sends it to a spinal cord stimulator. See, this is the monkey. It's dragging its right leg. And then the stimulator's turned on, and it's walking normally again. And when that stimulator goes off, it's dragging its leg again. Imagine if we could do that for people who had just been in a car accident or just had a stroke or a diving accident in a swimming pool, and we could rescue their spinal cords, right? So that's where this is going. But again, there's this issue. You have to do brain surgery. It's very invasive. What if you could get the brain-machine interface into that part of the brain without cracking open the skull? So this group in Melbourne had this great idea. They said that, well, we go through the groin. There are big vessels you can access through your groin. You just use a little numbing medicine. You don't need anesthesia for this. And we send things into the heart and into the brain, for instance, to help to coil aneurysms that have burst, and the heart to explode open ischemic clots in the heart that have caused a heart attack. There is a vein in your brain that overlies that motor strip. And they said, well, what if we take the same metal cage that we normally use and coat it with electrodes, send it up through the groin into the brain, and let it rest there? And that's what they did.
Hi, everyone. This is President Barack Obama. The US and Australia are funding research into a device that could someday allow people to control their prosthetics with their minds and without invasive brain surgery. When implanted into a blood vessel, this network of tiny electrodes can record your brain signals. Technology that has the potential to transform the lives of our wounded warriors and others with disabilities.
Okay, so if that's not extraordinary enough, now we're like crossing the line. How can we create the most clever brain-machine interface? So I introduce you to neural dust. So this also came out of the University of California at Berkeley. These are piezoelectric devices. So what these devices do is they transform energy from one form to another, from electricity to sound, from sound back to electricity. So why is that important? I can take this device, that's the real device wrapped around a nerve. I can stimulate the nerve from the outside using ultrasound and actually get it to fire electrically within. Or I can use it like a Fitbit. I can record electrical signals coming from the brain and the nerves, send it to the outside by translating it back into sound waves. Well, one of the scientists who helped to develop this, well, he got recruited by this guy, right? You guys recognize him, Elon Musk, right? Elon tends to put his money behind things that are huge, really important, but take a lot of capital to get started. And he was all over the idea of brain-machine interfaces. So that's why he founded Neuralink, okay, in March of 2017. And he took some of the top scientists who were working in brain-machine interfaces, including one of the co-scientists who developed neural dust. Now, he's been interested initially in actually the motor system. I know everybody talks about worrying about the AIs. He's actually interested in doing the really basic stuff first. But you can take these brain-machine interfaces, the same kind of things I'm showing you that can restore function to people who can't move, and you can actually use them to improve memory as well. And that's what this guy is interested in. Does anybody know him, Brian Johnson, from Kernel? So Kernel was founded before Neuralink. And Brian Johnson's big thing, he said this to me at a conference at Stanford last year. Why would we not be as ambitious about our own potential as we are about AI? And his idea was we should be focusing our energy on improving the human condition. Forget about the machines and the algorithms. So that's why he founded Neuralink. And here we are. This idea, this brain-machine interface market, $20 billion by 2027. By the way, I think this is an underestimate. I think this is an undervaluation because typically, most people don't understand exponential technologies, and when they're forecasting markets, they're usually off by an entire exponent, an entire order of magnitude. But brain-machine interfaces are not just the kinds of things I've been showing you. This next video comes out of Nissan. That is an EEG device. Same thing I use to measure consciousness. What are they doing? They're having drivers wear these EEG caps, and they're measuring the signals from their brain as they drive so that they can see what happens in the brain when the driver has an expectation that's met or that's violated, and they're using that and their reaction time to connect back to the car. Right? So they're creating what they think of as brain-to-vehicle technology, a different kind of brain-machine interface, but you can see how wide the applications are. Let's go back now to BrainGate, that same organization I was telling you about, that academic consortium that was actually working on creating the invasive brain-machine interfaces. It's not just for motor, it's not just for sensory. There are people who can't even speak any longer. Some of them have diseases like ALS, like Stephen Hawking, and he was using this weird synthesizer and eye blinks to actually communicate. Well, BrainGate actually, and by the way, she was one of my patients in the operating room. This woman actually is the fastest thought typist in the world. So she can type using her thoughts alone, because she's also paralyzed from the neck down. She can't use a mouse. And you can see what that looks like in this video. This is a different subject, and he's actually typing with his brain. You're going to see what that looks like. So that's just with his thoughts, not touching a mouse, not touching a keyboard. So these people can like surf the internet, right? The other woman who I showed you, she's been teaching herself to play musical instruments again because she was a musician before she was paralyzed. And so music is a really important part of her life. She also loves gardening, so she goes on the internet a lot to look for gardening supplies. So not to be outdone, I've already shown you Elon Musk, I've shown you Brian Johnson, so this guy says, hey, you know, people can start typing with their brains. What can we do with our social media? Same woman, right? So he's got her also. There's not that many subjects in the world that have had this device. It's experimental right now. But he's been trying to, in stealth, trying to get something where you don't have to like type into your devices to actually communicate with your social media. Well, there are companies, this is a startup that comes out of Canada. They've possibly beaten Zuckerberg. They actually have a device that uses a non-invasive EEG that can record the thoughts and intentions of a person who's paralyzed, who can't even speak, and interact with the internet, with Alexa, with the Internet of Things. We're already creating brain-machine interfaces that talk to computers and the internet. Imagine what doors that opens up. And that brings me also, by the way, to another subject. You got a robotics talk in the beginning of this session. Look where robotics is going when you combine them with all this. So this woman, Dr. Elena Garcia, she has a company called Marcy Bionics, and she's actually based here in Spain. And this is a video, they're actually creating pediatric, so for little children, exoskeletons for kids who can't walk properly. So you see the exoskeleton here, and then in the next clip, you're gonna see a child who's paralyzed in the exoskeleton that's moving, and the skeleton is actually helping to carry him forward. Now the key is you don't want to just always be attached to something that helps you move. What if you could use your thoughts to control an exoskeleton? And that's what you see here. This is from Miguel Nicolelis' group from Duke. He's originally from Sao Paulo. And he's wearing, this guy, he's paraplegic, so he's paralyzed from the waist down. He's wearing an EEG cap, and that cap interprets his desire to move, sends it to this bionic exoskeleton, which carries his legs forward. So he's using his mind to control a robot as well. But this robot happens to be moving him in space. Go back to Aaron's talk. This guy trains in VR, so he imagines moving, and an avatar shows him his legs are moving. So he's getting kind of feedback for all this. So the first extraordinary thing, in 2014, ooh, it's loud, this guy made the opening kick at the FIFA World Cup, paralyzed man, okay, using his mind. But this is much more extraordinary. It's just a simple article, the title I'm showing you, but let me explain what this is. So in the patients that Nicolelis took through this training protocol for a year, all paralyzed patients, he trained them in virtual reality, he trained them with this EEG device, he trained them with an exoskeleton, he gave them feedback. All 9 of these patients regained some neurological function. One of them was reclassified as no longer being paralyzed. So let me explain how extraordinary this is. None of these people had surgery, not a single one. No knife, no stem cells, no regenerative medicine, no CRISPR, no nothing. They imagined that they were whole and their nervous system repaired itself. We didn't even know that neurons could regrow. Here are people with spinal cord damage regrowing connections because they thought that the connections were still there. That's extraordinary. And imagine what each of you in this audience, each of you could do with that power of intention and visualization. And that's not been lost in the world. So again, I'm connecting back to our entire session. Aaron was talking about the power of virtual reality. Neural virtual reality is becoming a really important rehabilitation tool for people who have suffered injuries. And it's an important enough thing that one of the last unicorns that came out of Silicon Valley, MindMaze, is actually all about neural virtual reality. But let's go back to what they were controlling. Anybody know this guy? Anybody recognize him? Anybody seen him before? This guy is pretty famous. His name is Hugh Hare. I want you to take a look at his legs, or his lack of them. Right? He's got robotic legs. He's got bionic legs. He believes that the entire, not just people who have lost legs due to and have a disability, he believes all of us at some point will be embracing what he calls neuro-embodied design. And what does that mean? This is his bionics company. He has custom limbs that are created for everything, for mountain climbing, which by the way is how he lost his legs, for dancing, for running, for walking. So you get your own customized limbs, and certain advancements have to happen before these robots are ready for real time. So one of them is coming out of the Bow Lab at Stanford. She's been creating stretchable electronic skin for robots that can actually sense things. Take a look at this robot. It is so extraordinarily sensitive that when it touches this raspberry, it doesn't pierce it. It knows not to touch any further. That same sense of touch allows this robot to pick up really delicate objects and move them around. Now, the next thing that has to happen to close this system is that whatever is happening in the robotic arm or the robotic limb has to somehow get back into the brain. So that's what this guy, that's what this guy is doing. By the way, he actually got his PhD in Barcelona, so there's a lot of Spanish neuroscientists, by the way. So I'm going to let him explain what he's trying to do. So, volume?
Induces the same range of motions as the natural hand, but also induces brain patterns of activity that are similar to when a healthy person operates the hand.
So let me say that again for people who missed that. He's got an exoskeleton, but that exoskeleton is connecting back into not the motor cortex, but the sensory part of your brain. And it's letting the brain know what happened out there. Why is that important? I mean, I'm walking on stage. If I couldn't feel through my feet, even if my legs worked, I'd probably fall. We need to know where we are in space and time. And this has been taken to such a degree that this gentleman here, who is also paralyzed, is shaking President Obama's hand with a robotic arm. He's controlling with his brain, and there's a chip in his sensory cortex, and that is sending signals back to his brain so that he feels like it's his own hand that is touching Obama's hand. That's how he describes it, and that's the future. We're going to be creating these very sophisticated bionic limbs for people who are amputees or people who basically have lost neurological function, and we need those signals to get back into the brain as well as out of the brain. Now, what if you don't have the money for this very sophisticated arm? Well, you can go to 3D printing. You can take a phone and you can 3D image a stump and custom print a bionic limb. And eventually these limbs will be connected up to the brain. And that's why there's been an entirely new movement that's formed. This is from the Cyborg games, the Cybathlon. It's been going on for a couple of years, which allows people with disabilities to compete with these kinds of robotic prosthetic devices. But remember the ethics? Remember what Anita talked about in the first talk? Don't give a robot or an AI a machine gun. Okay, well, this is a bionic appendage that's been attached to a machine gun to allow a soldier to balance that better, right? But all the militaries in the world that we have assayed at the moment are developing super soldier capabilities, all right? And then when you connect that up with the brain-machine interface capability, we need to all be talking about this, right? This isn't something we should just leave up to governments to talk about. We need to be talking about what we want as a society. Now, this brings us to like one of our final topics, right? I asked you to think about, do you guys remember who raised their hands when I said, would you take an implant to improve your ability to play the violin? I don't know if any of you have changed your mind during this talk for either direction. but this guy, Neil Harbison, he's actually got something. This is implanted in his skull. This is a camera. It's a multispectral camera. It images the world in a wider range than our eyes can see. And every time that camera looks at something in the world, it vibrates in his skull and he hears it. It's like a synesthesia of sorts. So if he were looking at, say, your face, he would hear almost a musical composition that would go with your face every single time. So that's how he moves through the world. And he's founded an entire augmentation movement. This is his friend Moon. She's a dancer, but she's got seismic sensors in her feet. She can feel earthquakes, right? So she can move to that. See some other things. This is something called Skinput. You can see here a hierarchical menu that is embedded in someone's forearm, right? So they can use this to interact with all kinds of devices. So this person's now making a phone call. That's a New York number. And look at this, it's a hierarchical menu. And what's happening is that he's inducing all these vertical waves that are being sensed by the sensor he's wearing around his bicep. People like this guy, Kevin Warwick, he's implanting all sorts of devices, off-label, on-label. He's put RFID devices in so he can like turn on lights and HVACs and open his door with just like waving his limbs in front of them. This guy is using biomimicry to improve his ability to run fast, right? So he went for inspiration in nature to the fastest bipedal animal, the ostrich, and he created a set of bionic boots that look like ostrich legs. And he's running at, I think it's something like 40 to 50 kilometers an hour using these bionic boots. It's absolutely insane. So that's kind of where we've moved to. And if you think that people wouldn't do that, nope, there are people writing all sorts of op-eds. I would replace my right arm with a robotic one. Would you? Would you? That's the question, right? And that's what I'm saying. We are moving into this area of the augmented human. And on top of it, we're editing our brains, right? CRISPR, I don't have time to explain the actual process, but has everybody heard of CRISPR? Show of hands? Okay, so I'm going to say about half of you, let's just leave it to say, we now have the ability to read DNA, find errors, cut them out, and replace them with the right sequence. Okay, so it's like in your Microsoft Word document, it's like the command find and replace function. So you can repair these gene misspellings, and you can see that the very first clinical trials, January 4th, 2019, this is actually a European trial for sickle cell disease. There's going to be also one coming online to treat cancer and T cells. But the big risk here, ethics, everyone. What if we edit our germline and create designer babies, create babies that are smarter, taller, have a certain skin color, eye color, intelligence? Well, we thought that this was some scary science fiction thing, and at the end of last year, this happened. A Chinese researcher went ahead on his own without anyone's ethical permission and edited 2 twin embryos using IVF and reimplanted them. The first CRISPR babies are already going to be born. We've already edited humans, and they are born, and we're going to find out what that means, right? And in this whole process, we're editing brains, we're writing brains. Hey, we can now regenerate brains. Did you know that you can actually use cellulose, the material that comes out of fruit and vegetables, to create scaffolding to make new organs? Okay, so we can like 3D print on top of this kind of scaffolding, and that's going to be the future. Well, we're here talking about the nervous system. University of California, San Diego, just last month, printed the first hydrogel to do a spinal cord repair that can be inserted into a person with a spinal cord, like basically a severed spinal cord. And if that's not weird enough, these companies, cryogenic companies, how many of you have thought about freezing yourselves so you can live forever or be woken up later? Anybody? Any takers, freezers? A few? I mean, okay. How many of you would do it if your brain would be damaged by ice crystals? Has anybody ever put like ice cream in a freezer and then taken it out and put it back in and it's disgusting? This woman is the co-founder of one of those companies. Fred's last word, she's hugging her husband who's already in a cryogenic vat. Gee, I hope this works. Okay, so here are the companies. This is the exponential curve. Towards the end of the 80s, people started putting money down to freeze themselves and be woken up. And there are companies founded to actually reanimate brains, okay? So they're actually working on this technology. The head of one of the biggest accelerators in Silicon Valley, Y Combinator, put down money to freeze his brain already. So people are there. They're gonna do it. And has anybody thought during my talk, hey, you're connecting brains to everything else. Can you connect brains to others? Anybody wondering about telepathy? Telepathy, anyone? Right? Why not? Okay, so artists think this is kind of cool. So they're trying to create these fused brain-machine interface things to create art. I am here to tell you that the first non-invasive telepathy experiment has already been done. 2014, somebody here sending a thought using bits, using an EEG device, somebody receiving it, doesn't matter where, another country, the next room, over the internet. There's a magnet at the back of the head, non-invasive neuromodulation, stimulating his brain and letting him know what the other person was sending. And then at the end of last year, the first three-way social network was formed with a connection of brains playing Tetris. And then in December of last year, I mean, everything is happening so fast. The first brain-to-brain interfaces have been created to decrease the cognitive load. I mean, imagine what would happen. Hey, if you and I connected our brains, how much easier would it be to solve problems? Now I'm going to add you and you to that network. What would a brain-to-brain, what would the whole room connected look like? Right? That would be extraordinary. And that's why we're going to end with this finally. Can we create brains from the ground up? Could we simulate a brain, every nerve cell, every connection from the ground up? And would we get something that expresses consciousness? This group in Switzerland has been trying to do that. They've got brains in a dish that are firing like brains. But the craziest thing just happened. Induced pluripotent stem cells, you can take skin and fat cells from people now, put them in a dish, revert them with chemicals, turn them into something else. People have been doing this now to create mini organs. You can create mini brains in a dish using adult stem cells, not fetal, adult stem cells. And the first one at the end of last year, November 2018, started firing like it was a premature baby brain. I just told you we grew a brain in a dish, okay? A brain that fires like a baby, fires like a premature baby. Is this thing gonna start expressing consciousness? I mean, forget machines expressing consciousness. Are we gonna start growing consciousness in a dish, right? So back to the mapping, right? This human connectome. If we could map every connection in your brains, would we produce something to look like you? We did it in a worm. Only 306 nerve cells. Put them in software, create a Lego robot. You can actually get that Lego robot to respond to stimuli from the outside world like it's a worm. It's a worm. It has all the worm brain stuff. It's a worm. That thing thinks it's a worm. Okay? Just saying. So what have we done? I have taken you this huge journey, right? We've talked about brain mapping. We've talked about editing brains. We've talked about growing new brains. We've talked about electroceuticals. We've talked about robotics. What else have we talked about? Oh, a little stem cell regeneration stuff, some brain-machine interface stuff, some cognitive enhancement, finally ending with human enhancement. And so I want you to hold these two questions. Will connecting humans to machines make us something more than human? Okay? Think about this. Are we going to start speciating? Will we be human anymore? And here's your second question. If we build sufficiently complex machines, will that allow them to express that thing that we call consciousness? So that we may end up with friends who look like this, or look like this and don't even know that they are different from us. Because we've already done this, connected our brains to the internet, we're already connecting brains to brains, and one of these days we may get to the point where we can isolate your brain and have you potentially live forever. So with that, I thank you. Gracias.